Welcome to Solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Now, virtual work. For this particular problem, we want to determine the angle theta for equilibrium as the spring is stretched. Okay. To solve this problem, we will apply the virtual work principle. Okay. We have a spring at this point between A and B, and the spring force here is coming at A is this helps us with S, and the spring force here is this helps us with S. Okay, and the displacement here for this one is the X source with A. You can see that this one is acting, the displacement and the force there are in the same direction. So let me just put it here. So it's X, the X source with A with small virtual displacement. Okay, and for here we have the virtual displacement here is not acting, sorry, the force is not acting in the same direction as the virtual displacement for B. So the virtual displacement is acting in this direction for B, and is let's call it the X source with B, and there's a force here P. Okay, let's call the virtual displacement acting, this is point C, as the X source with C. Okay, these are datum E, this line ED. Now all the lengths are between the linkage between here and here, here to here, here to here. They are all 0.2 meters. For example, look at one. This is 0.2, 0.2 meters. Same goes for the other ones. Okay, so that when we are solving, so that's what we have there, something like that. Okay, and this is our theta, angle theta. Now we can just to solve the problem, we apply virtual work principles. We will determine the virtual work due to P, so that the virtual work due to the spring force, the spring force, and apply them into the equation to solve for theta. All right, for the spring, we can determine the position coordinates at A with respect to fx, the suffix s at A is going to give us 0.2 sine theta. Sorry, 0.2 sine theta. Yes. Okay. Then, if we take the derivative of this and just make the x of A the subject of the formula, the derivative with respect to theta, the derivative of x sub A with respect to theta, and make this the subject of the formula, we're going to arrive at 0.2 cos theta d theta. Okay, so you have that. Now you can do same for the spring as well at B. the position coordinates, specifying the force F subscript S at B. So you are going to have it to be three times that. Just check the configuration of the diagram there. You will see that you have the 0.2 3 times 0.2 sine theta. So when you also take the derivative and make the x substrate b the solute of the formula, you're going to arrive at 0.6 cos theta d theta. Okay, so that's what you are going to have there. All right. Now we can consider the spring force. For the spring force, we are going to have something. We know that F substitute S is equal to the spring force. Sorry, is equal to the spring stiffness times X. Right. So which is still the same thing as saying is equal to the spring stiffness is given at 15,000. Sorry, 15 kilonewton. We say now 15,000 newton, 15 kilonewton per meter, which is 15,000 newton per meter as well. So if we consider uh, the displacement, okay, we are going to have it to be 2. And of course, remember that this spring is being extended, okay, so it's going to be 2 sine theta, which we do not know, all right, okay, minus sine, sorry, 0.2 sine 15 degrees, which is the angle when the spring was unstretched. So you are going to have that, all right? So if you just bring everything out, you are going to arrive at 6,000. 6,000. Okay, 6,000 sine theta minus 1,552.91. Okay, so that's what we are going to have as a force, Newton. All right. Now we can just also look at P. If we consider P, we have for P, the position coordinate specifying P is going to give us S of C. Okay, is equal to, of course, this one is going to be 8 times. Just check the diagram. It's going to be 8 times the length of what we have for X of A. 0.2 sine theta. Okay, so that's what we are going to have now. So if you just take the derivative of X of C with respect to theta, you are going to arrive at and make X of the X of C just the solid of the formula straight. You are going to arrive at 1.6 cos theta d theta cos theta d theta. Okay, so that's what we are going to have. All right. So having gotten all these ones, okay, we can just go straight and apply our equation, which is the virtual work equation, okay, which is this equal to 0. So if we do that, we are going to arrive at, for the first force, okay, it's going to give us F, the X starts with A, okay, minus F. So this is negative virtual work because the force is opposing the virtual displacement, the, the direction. So we have this, okay, plus P, the X of which so everything is equal to 0. So if you plug in values into it, we are going to arrive at 6,000. Okay, just plug in all the values into it. If you do that, you arrive at minus 2400. Okay, sine theta cos theta. Okay, cos theta. Okay, okay, plus 1. Okay, plus, okay, 62121.17 on 7 cos theta, cos theta, the theta, all right, plus 960, plus 960, 960, okay, cos theta, the theta, cos theta, the theta equal to 0. Now you can see that cos the theta is common, so but it's not equal to 0. So when you solve the equation, you are going to arrive at theta to be equal to 41. Of course, you will take the arc sign, okay, of whatever value you get when you do your division, and have this as your angle. So see, this is the angle for equilibrium when the spring is stretched. Okay.